Hello and welcome to Mr. Linford's Math 097 course. This is a presentation on section 4.4 of the text. In this section, they're talking about applications to systems of equations, in particular, systems of equations in just two variables. But today we're going to be focusing on just one of the applications, and that is uniform motion. And in particular, we're going to be talking about airplanes. So, uniform motion, the big idea here to remember is that distance equals the rate at which you're traveling times the time that you're traveling, how long you're traveling at that rate for. Now, uniform motion is this idea that we're going to make one trip and then we're going to come back. So we're kind of doing a round trip. And we're going to study the differences in the fact of speed. And we're going to see how our rate's going to be kind of different as we go in both directions. Now, in this problem, we're starting from Atlanta and we're taking a flight out to Los Angeles. So we're going to go from Atlanta in Georgia all the way out to the west coast, LA. And that's going to take us about 5 hours. And then we're there for a little while and we're going to come back. From LA, we're going to fly all the way back to Atlanta. But this time it only took us 4 hours. Now, in the problem, we say that the distance between Atlanta and Los Angeles really is 32,000 kilometers. That distance doesn't change. What's unique though is that our times were different. It took us an additional hour when we were heading out to LA, but we were able to go much quicker on our way back to Atlanta. And we often are wondering, well, what's affecting that? What's affecting our speed? Why does the plane travel at the same speed all the time? Well, what's interesting here is this idea of wind. Wind is this external force, this external factor that's going to play in, and what it's doing is it's affecting our speed. So when I fly from Atlanta to Los Angeles, I'm flying against the wind. The wind is blowing in this direction. So we're going to say, if you know your geography, it's going from the west to the east. So it's blowing towards Atlanta. So if you can imagine, I'm in some plane here. That is a terrible drawing of a plane. But, we're flying along, and, the plane's engines thinks it's going some speed, and then all of a sudden this wind starts coming in. This wind comes in, and it's pushing us back. It's pushing against us. If you've ever walked against the wind, or if you've ever been in a kayak or a canoe, and you can feel the wind pushing against you if it's a stormy day, then you know for a fact just how strong that can be. So the wind's going to slow us down a little bit. It's not going to prevent the plane from flying, but it'll slow it down a tiny bit. And so what we're imagining here is that our plane, the speed of it is being slowed down as we go to LA. But then on the same note, as we go back to Atlanta, the wind, as we say, is at our back. It's called a tailwind. The wind is now pushing us. We are in some plane, and then the wind comes in and it pushes us. It gives us some speed. Now, if you imagine just making a paper airplane and then throwing it and having a fan behind it, oh yeah, it's going to go much faster now. So what we want to do is we want to make two equations. One equation for the first trip and another equation for the second trip, and we're going to use distance, rate, and time to model both equations. Now here's equation 1. The distance, well, that's 32,000. The rate, well, I'll come back to that in a second. Let's start with the time. So I'm talking about the first trip here, trip 1, going from Atlanta to Los Angeles. Well, that took me 5 hours. Now let's imagine what my rate was. Well, let's say that P is the speed of the plane, how fast that plane's going. So I could say, okay, well, however fast the plane's going, that's my speed. But wait a minute, something's affecting the plane and the speed. I'm not really going what I think I'm going. The plane's engines think it's going, a certain speed, maybe 400 miles per hour. But the problem is this external force is pushing against the plane. So the plane's engines might think it's going, say, 400 miles per hour, but the wind might be slowing it down a little bit. So what we're going to say is the real speed that we go is whatever the plane thinks it's going minus how much the wind is slowing us down. This right here is how fast we're actually going. We have the speed of the plane, and then we also have the speed of the wind to worry about. The wind is going to slow us down. That's what we need to take into consideration. So for the second trip, my distance is still the same. I still covered 3,200 miles, but this time it only took me 4 hours because my speed was the speed of the plane plus the wind. The wind pushed our plane along just a little bit more, enough to cut our trip down by an hour. So these are the two equations that we need to solve. Okay, when we're going to go and solve these equations, typically what students would do is they're going to try to distribute the 5 through into the parentheses, distribute the 4 through into the parentheses, because they're good students. They know, hey, I got to clear parentheses before I move forward, which is a good idea. You are totally allowed to do that. And then you're going to have to do elimination, possibly, or substitution to clear this. What I'm going to recommend instead, and I'm going to do this as a little side note, so I'll change colors here. What if we took 32,000 equals 5 times p minus w, and instead of distributing 5, what if I divided both sides by the 5? What would happen here? Well, that would cancel out, and 32,000 divided by 5 is 640, and so, what are we left with? 640 equals p minus w. Well, let's see, that's actually much easier to work with. So I have now coefficients of 1 here for the p and the w. That's much easier to work with. So it turns out we don't really need to go ahead and distribute. You can if you want to, but we don't have to. So let me clear what we just wrote here. Let me clear this side work. And then let's see what would happen if we went and divided these numbers over. Let's divide the 5 over and the 4 over. So my first equation, when I divide the 5 over, we said turns into 640 equals p minus w. And then if I divide the 4 over, we should get the second equation to be 800 equals p plus w. This is much easier to solve. I'm going to do the addition elimination method. And what do you know? I'll change colors here. The w's cancel out. And what are we left with? Well, p plus p is 2p. And 800 plus the 640 should give me 1,440. All right. Divide both sides by 2. And we should, if everything was done correctly, end up with p, the speed of the plane, is 720 miles per hour. Or I should say, I'm sorry, kilometers per hour, since we're dealing in kilometers. So this plane is going 720 kilometers per hour, or at least it thinks it's going that speed. Don't forget, the wind is going to slow it down just a little bit. So the engines think it's going 720, but how fast is the speed of the wind? How fast is that affecting it? Well, let me change colors again, and let's try and figure that out. Now that we know p, I could plug p into, say, this equation. That is a terrible star. I promise I'll get used to the stylus at some point. Or I could plug it into this equation. So we could plug p into either of these. But gosh, that would be kind of messy to solve, and I don't know, I'm feeling really lazy. Why don't I try plugging p into one of these equations? Because these are the same thing as this. We just simplified it. These pair of equations are the exact same. It's the exact same system. We just simplified it a little bit. So I'm going to go and I'm going to plug p into, I don't know, maybe this one right here, number 2. That seems a lot easier to work with. So let's see what happens there. If I plug p in, I get, let's see, 800 equals 720 plus w. Sorry, I'm running out of room. So if I subtract 720 from both sides, I end up with 80 equals w. And that should work. So the speed of the wind is 80 kilometers per hour. So there we go, we got our system. we have it solved. We figured out that the plane thinks it's going 720 miles per hour, and the wind is going 80 miles per hour. So when I fly from LA to Los Angeles on this first trip, my plane thinks it's going 720 kilometers per hour, but in reality, it's actually going 640 kilometers per hour because it's slowed down. And when we go back to Atlanta, when I have a much shorter trip, the plane thinks it's going 720, but in reality, the wind's pushing it an additional 80 miles per hour. So we're going 800 kilometers per hour. I know I keep mixing up miles and kilometers. I'm bad about units. But the point of this is that we have some external force affecting how fast we are actually moving. It's affecting our rate. And this is the idea of uniform motion. We've covered the same distance twice. This distance right here did not change, but the way we covered that distance did change. We had a different time and we had different rates. Let's apply this idea again to a similar problem. This time, we're in a plane that flies from Detroit to Los Angeles. I don't know why we keep going out to LA. I don't know. Maybe I'm thinking of warmer weather. So we're going from Detroit to Los Angeles. And this time, when we go to LA, we are flying against the wind. So the wind typically moves from the west to the east. So we're flying against the wind. Let's draw a little picture here to see what's going on. Here's Detroit. Here is LA. I always like to do little sketches of this just to keep all this information straight. So we're going from Detroit to LA on this first trip, and it takes us about 4.9 hours. Oh, we got decimals to deal with here, but you know what? That's okay. We'll make it work. We have 4.9 hours. The return trip back to Detroit takes 3.3 hours, so it's going to be shorter. Time equals 3.3. Okay, now notice here it says tailwind. Wow, just crossed through that. It says tailwind. So that means the wind's at our back. And when we go to LA, it is flying against the wind. So the wind is moving from LA to Detroit. It's blowing in this direction. I will always draw little arrows to point to me where the wind is going, just so I know when I'm going fast or when I'm going slower. Now the distance between Detroit and LA, that doesn't change. It's about 3,190 kilometers. So right now we have all the information we need to set up two equations. The first equation will be for the first trip. The distance is 3,190 kilometers. That's going to equal, let's take our time. On the first trip, it took us 4.9 hours. And the speed of the plane was, well, I'm going p miles per hour or p kilometers per hour in the plane, but the wind is slowing me down. So I'm going to subtract w. This right here is how fast I'm actually going. For the second trip, I am still covering 390 kilometers. 3,190 kilometers. But this time I'm going to be traveling for much shorter, 3.3 hours, because though my time went down, my speed went up because the wind is at my back. It's pushing me a little bit. Now, this looks kind of messy. I don't really want to distribute decimals because, well, who does, right? Who wants to work with decimals? So we could do a couple things. We could try to clear the decimals, which, you know, that wouldn't be too bad. I could try to divide them over, and if I did that, I'd get a very long decimal, probably a repeating decimal. So I'm thinking, you know what, let's just divide this over and round. We're going to be doing some approximations with our mathematics, but you know what, that's okay. Otherwise, I could just clear the fraction, but hey, if I want to use this division technique, I'd have to deal with that long decimal anyway. So let's pretend like we're going to divide 4.9 from both sides. So let's divide that over and see what we get. And I'm going to write this in blue. So I go ahead and divide this over, and I'm just going to round this to the nearest decimal place. So let's just say 651 equals P minus W. It's really 651.020408. I don't feel like being too accurate. And then what we're going to do is we're going to divide the 3.3 over. So when I take 3,190 and divide 3.3, I'll get, let's say it's about 967 equals P plus W. So when I go ahead and combine these, the W's are going to cancel out. I'm left with, very little room. So let's take 651 and 967. I will get, I'll move this work over here, 1,618 equals 2p. Divide both sides by 2, and we will end up with about 809 equal to p. So the speed of the plane is about 809 kilometers per hour. To figure out the speed of the wind, well, let's just plug it into one of these equations. We could plug it into one of these, or we could plug it into the more simplified ones. I'm going to say let's go into the more simplified ones. So I'm going to take 967 equals, instead of saying p, I'm going to plug in what it equals, 809 plus w. Well, let's subtract this from both sides. And let's go ahead and solve for that w. So 967 minus 809 should be 158w. That should be the speed of the wind, and whoa, that is moving quickly. So 158 plus the 809 times 3.3, and when I do that, we end up with 3,191.1. Wow, we were only off by 1 kilometer per hour, which isn't that bad at all, actually. That's a pretty fair way of working through this problem. So in this one, we did the exact same technique, and it's important to know that we can divide this number from both sides, and we end up with something much easier to simplify. That's the goal of this technique, being able to cancel out the wind. And just work with the speed of the plane. That's something that's super beneficial. Now, if you wanted to, you could go ahead and distribute this through. That's totally fine. It's totally allowable. It'll get a little messier, but, you know, nothing wrong with that. I'm sure you'll be able to work with that, okay? Now, that's the big idea with these two problems. This Batman problem, go ahead and give it a try on your own. We talked a little bit about it in class. It's going to require some rounding as well, but that's okay. Nothing too bad about that. I would say round it to the nearest kilometer per hour, the nearest kilometer. Basically, don't worry about any decimal places with this one in particular, because the accuracy that we get from just rounding it to the nearest whole number actually isn't that bad. Alright, so in this talk, we discussed the idea of uniform motion, how to set up the two equations for it, and in particular, how to work with this idea of wind and wind affecting us. Now, this setup is going to be the same thing for when you see problems. You know, oftentimes they do airplane problems with uniform motion, but other times too they do boat problems. So you're in a kayak and you're paddling against a current. Well, this is the exact same idea, except instead of P and W, I'd say B for the boat and C for the current, right? It's the same setup, same idea. The key idea that we're working with here is distance equals rate times the time. Just remember that and be able to say, hey, my rate here is being affected by some external force. And if you can come up with that, and maybe remember this little simple technique that we came up with to get two very simple equations to solve, then you'll be all set. If you have any questions, feel free to email me. My email is klinford, KLINFORD, at wccnet.edu. Let me know if you have any questions or comments, and if this was helpful. Until next time, take care.